then you'd be right there. You'd have to have, well, I guess as long as you say this, the sup of f plus g is less than or equal to sup f plus sup g. And the inf of f plus g is greater than or equal to the inf of f plus the inf of g.
You have to subtract those things, right?
So this minus this, yeah. And then separately you have this minus that. These are controlled. Yeah, okay, I'm believing it now. It's all, these things just drive me nuts because I can't remember. You know, if you have something like sup of f minus inf of g, is that, which direction is that relative to this and to this? You know? Write all those inequalities down and prove it. I never remember that stuff. These two I know. That's pretty obvious. One, you know, can you give me a k square is strictly less? Well, if f equals g, this is twice and that's twice. So that's okay.
Sine cosine. Sine cosine.
Supremum and sine and cosine added together. That be 2 is less than or equal to 1 plus 1. I don't know. I think you can do it this way. Yeah.
Because you have a less than or equal to this side.
Yeah, oh right. I mean, if you subtract these things, this is what you want. You want that times delta alpha summed up over the partition to be small. And you have this minus this summed up, and this minus this summed up small.
Oh.
So yeah, I think you could do that. Sure. Well, anyway. And then you guys, if you had it on the final, you could show that multiplication by a constant, if f is even still just integral, then c times f, where c is a constant, would be, that'd be pretty good. And then, Cindy, you would start out with fixed epsilon over c. Yeah. Write that one down. Write that down. Okay. Well, all right. Were you, Dave, were you here when we did a couple of problems in, like exercise set 4.3.2? Were you here when we did that? On page 80, 4.3.2. I just wanted you to see that. Well, here, you want the Riemann-Stieltjes just integral. We did this. No. Were you? This is the greatest integer function? Yeah. How do we do it? We used integration by parts, right? Turn it around. They used the theorem on the previous page. Okay, just keep that in mind too. That's a good thing. Okay. Let me see if they have a cute problem that has to do with Euler's formula. Yeah. That always kills me. I'm looking at the theorem 4.5.1, which Dave's going to explain to us on Thursday. So you can ask questions like exercise 4.5.1. Anybody want to take a stab at the exercises there, 4.5.1? The sign of the square root of n over n. Well, we know we don't know anything. We start at 1 and go to infinity. Sine n over, oh, jeez. Hang up, no. And then exercise 4.5.2 is an estimate for the Euler-Mascheroni constant, which is
Oh, yeah. Yeah, I know.
I used to know what it was too, maybe 20 places now I don't. Sorry. Getting old. Anyway, okay. Whitney, do you want to do the Volterra thing, and then I'll finish up with the Leve's thing. Or not, if you want me to do it first. Okay. Well, here, you want my pen or yours? You can write your own stuff. Okay, so we're gonna do the Volterra example, and the reason it is so important is that it showed that the Riemann integral had a basic defect. It could not integrate bounded derivatives, which nobody had expected or suspected up to that point. And it inspired Leve some 20 years later to invent the right around 1900 was a period of great sort of ferment in the integration business. There were a lot of really smart guys considering new integrals and new measures and that sort of thing. It was a raft of new ideas. 4 or 5 new integrals defined. Stooges, Leve, Delon, Getting Joy, Young, and Young. These are all people working. A lot of those integrals are equivalent. It's another way of getting maybe it's really fast. Or it's kind of a chapter. But the whole thing about measure and signal and stuff, you don't have to worry about that. You just think that you operate from someone after making these big stuff. You don't like measure theory per se, science study, and still have what they equal to. So, okay, I'm sorry,
That's okay.
rambling here.
Got the one from the book, but also somebody else, somebody actually did a lot of work already. A teacher that had some really nice graphs. So
Where'd you get them? Oh, is this on an internet thing or?
Yeah.
Oh, I see, okay.
this is page 70 on the book. I don't know if that's as clear as it's going to get from here. The Volterra example, basically, what it wants to do is show you that something's differentiable and not continuous. So at the end, basically, they're going to say that the partitions are greater than epsilon. So the way the book does it is they're using the Cantor set, and they're letting C denote the Cantor set of positive measure. And then this I and K, it's an open set of one of the removed intervals from the Cantor set. We talked about Cantor set a couple of times already, so.
This isn't the middle third set, though. This is the middle half set, or middle quarter set, isn't it? You can't take out the middle third because then you don't have any measure left. So this is one of those. Remember on the practice exam I said Smith Volterra Cantor?
Yeah.
This is the first one of those.
And I think it's the same set that we did, that you explained last class.
Yeah, we took out the 1/2 centered on 1/2, right? And then we took out 1/4 centered on 1/4 and 3/4. We kept going. So we took out in total. How many did that one? I need to wind up with a 1/2. I'm sorry, I didn't mean to distract you. It'd be nice to know exactly what this, how you get this set. He said